So what you saw there is really quite close to what we will actually build. It will look almost exactly what you saw, like what you saw. So this is not an artist's impression. These the simulation was actually made from the SpaceX engineering CAD model.
Estos ya se hicieron con el sistema de CAD.
It's not just, well, this is what it might look like. This is what we plan to
vamos a
try to make it
ver.
look like.
Y en realidad va a ser casi igual, ¿eh?
So in the video, you got a sense for what the system architecture looks like. The rocket booster and the spaceship take off, loads the spaceship into orbit. The rocket booster then comes back. It comes back quite quickly, within about 20 minutes. And so it can actually launch the tanker version of the spacecraft, which is essentially the same as the spaceship, but filling up the unpressurized and pressurized cargo areas with propellant tanks. So they look almost identical. So this also helps lower the development cost, which obviously will not be small. And then the propellant tanker goes up, and it'll go up multiple times, so anywhere from 3 to 5 times to fill the tanks of the spaceship in orbit. And then once the spaceship the tanks are full, the cargo has been transferred, and we reach the Mars rendezvous timing, which, as mentioned, is roughly every 26 months. That's when the ship would depart. Now, over time, there would be many spaceships. You would ultimately have, I think, upwards of 1,000 or more spaceships waiting in orbit. And so the Mars colonial fleet would depart en masse. They're kind of like Battlestar Galactica. You've seen that thing. That's a good show. So a bit like that. But it actually makes sense to load the spaceships into orbit because you've got 2 years to do so, and then make frequent use of the booster and the tanker to get really heavy reuse out of those. And then with the spaceship, you get less reuse because you have to say, well, how long is it going to last? Well, maybe 30 years. So that might be 12 to maybe 15 flights of the spaceship at most. So you really want to maximize the cargo of the spaceship and reuse the booster and the tanker a lot. So anyways, the ship goes to Mars, gets propellant replenished, and then returns to Earth. So I'll go into some of the details of the vehicle design and performance. And I'm going to gloss over, I'll only talk a little bit about the technical details in the actual presentation, and then I'll leave the detailed technical questions to the Q&A that follows. This is to give you a sense of size. It's quite big. And yeah. I mean, the funny thing is, I think in the long term, the ships will be even bigger than this. I think that this will be relatively small compared to the Mars interplanetary ships of the future. But it kind of needs to be about this size because if in order to fit 100 people or thereabouts in the pressurized section, plus carry the luggage and all of the unpressurized cargo to build propellant plants and build everything from iron foundries to pizza joints to you name it. But we need to carry a lot of cargo. So it really needs to be roughly on this order of magnitude because if we say like say a minimum threshold for self-sustaining city on Mars or civilization would be 1 million people. Well, and you can only go every 2 years. If you have 100 people per ship, that's 10,000 trips. So I think at least 100 people per trip is the right order of magnitude, and I think we actually may end up expanding the crew section and ultimately taking more like 200 or more people per flight in order to reduce the cost per person. So, but it's 10,000 flights is a lot of flights. So you really want ultimately, I think, on the order of 1,000 ships. It'll take a while to build up to 1,000 ships, and so I think if you say when would we reach that 1 million person threshold from the point at which the first ship goes to Mars, it's probably somewhere between 20 to 50 total Mars rendezvous. So it's probably somewhere between maybe 40 to 100 years to achieve a fully self-sustaining civilization on Mars. So that's the sort of a cross-section of the ship. And in some ways it's not that complicated, really. It's made primarily of an advanced carbon fiber. The carbon fiber part is tricky when dealing with deep cryogens and trying to achieve both liquid and gas impermeability and not have gaps occur due to cracking or pressurization that would make the carbon fiber leaky. So this is a fairly significant technical challenge to make deeply cryogenic tanks out of carbon fiber. And it's only recently that we think that the carbon fiber technology has gotten to the point where we can actually do this without having to create a liner on the some sort of metal liner or other liner on the inside of the tanks, which would add mass and complexity. So it's particularly tricky for the hot gaseous oxygen pressurization. So this is designed to be autogenously pressurized, which means that the fuel and the oxygen, we gasify them through heat exchanges in the engine and use that to pressurize the tanks. So we'll gasify the methane and use that to pressurize the fuel tank, gasify the oxygen, use that to pressurize the oxygen tank. And this is a much simpler system than what we have with Falcon 9, where we use helium for pressurization and we use nitrogen for gas thrusters. In this case, we would autogenously pressurize and then use gaseous methane and oxygen for the control thrusters. So really, you only need 2 ingredients for this, as opposed to 4 in the case of Falcon 9, and actually 5 if you consider the ignition liquid. So we use a sort of complicated liquid to ignite the engines that isn't very usable. In this case, we would use spark ignition. So this gives you a sense of vehicles by performance, sort of current and historic. If you can actually read that, but in expendable mode, the vehicle approach that we're proposing would do about 550 tons and about 300 tons in reusable mode. That compares to Saturn's 5 max capability of 135 tons. But I think this really gives a better sense for things. The white bars show the performance of the vehicle, like in other words, the payload to orbit of the vehicle. So you can see essentially what it represents is what's the size efficiency of the vehicle. And most rockets, including ours that are currently flying, the performance bar is only a small percentage of the actual size of the rocket. But with the interplanetary system, which will initially be used for Mars, we've been able to, or we believe, massively improve the design performance. So it's the first time a rocket's sort of performance bar will actually exceed the physical size of the rocket. This gives you a more direct sort of comparison. This is the thrust level is quite enormous. We're talking about a liftoff thrust of 13,000 tons. So it'll be quite tectonic when it takes off. But it does fit on Pad 39A, which NASA's been kind enough to allow us to use, where they somewhat oversized the pad in doing Saturn V, and as a result, we can actually do a much larger vehicle on that same launch pad. And then in the future, we expect to add additional launch locations, probably adding one on the south coast of Texas. But this gives you a sense of the relative capability if you can read those. But yeah, these vehicles have very different purposes. This is really intended to carry huge numbers of people, ultimately millions of tons of cargo to Mars. So you really need something quite large in order to do that. So talk about some of the key elements of the interplanetary spaceship and rocket booster. We decided to start off the development with what we think are probably the two most difficult elements of the design. One is the Raptor engine, this is going to be the highest chamber pressure engine of any kind ever built, and probably the highest thrust to weight. It's a full-flow staged combustion engine, which maximizes the theoretical momentum that you can get out of a given source fuel and oxidizer. We subcool the oxygen and methane to densify it. So compared to when propellants are normally used, they're used close to their boiling point in most rockets. In our case, we actually load the propellants close to their freezing point, and that can result in a density improvement of up to around 10 to 12%, which makes an enormous difference in the actual results of the rocket. It also makes it gets